webinar. My name is Ollie Walsh and I'm the chairman of the BERAAI Association. I think this is an area that you'll all find really interesting. It's a real growth area. So I'll introduce you to Mike Teahan. Mike is a highly qualified independent expert on heating, cooling and ventilation. He's highly regarded within the construction industry as one of the leading advisors on renewable heating solutions for both residential and commercial projects. He's an expert in heat pump technology. He's been involved in design, supply, install and commissioning of several thousand heat pumps, including award-winning domestic and commercial systems with SEI. He's fast becoming the go-to person for exhaust air heat pumps solutions for apartments, buy-to-let and student accommodation development projects. We expect the seminar to take about an hour, and we'll allocate time at the end of that for questions and answers. So if you have any questions, there's a Q&A facility. You're probably all familiar with it at this stage on the side there, so you can just type in your question there and we'll address them. We may address some as we go along, but ideally we'll address them all at the end. So maybe without further ado, I'll hand you over to Mike and we'll get straight into it. Mike, I'll pass it on to you there.
Good stuff. Thanks, Ollie. Everyone, welcome. Mike Teahan is my name. Thanks, Ollie, for the introduction. My head isn't big enough. It's big enough now, anyway. That's for sure. Anyway, so today's topic is exhaust air heat pumps, and I suppose towards the end of it would be kind of the most important part where you guys are involved in BR assessments, where we go through screenshots of how the exhaust air heat pumps slot into the DEAP program. It took a long time for SEI to make us, I suppose, provide a methodology to allow exhaust air heat pumps fit into DEAP, and as you know, those wheels turn very slowly. So with the last 12 months or so, we've been tweaking it with SEI along with likes of Ollie and lads getting involved to present questions to SEI, and they give us a definite roadmap now how to slot in the exhaust air heat pumps into DEAP. Also at the very end, I want to quickly, if we have time, to go through a very, very important point with exhaust air heat pumps is what is the true and real output of an exhaust air heat pump. For example, if you took a Hitachi or a Daikin or a Samsung or Mitsubishi split or a Thermi or an eBay, whatever it is, heat pump, and the badge says 9 kilowatts or 8 kilowatts, you can be damn well sure that's a 9 or an 8 kilowatt heat pump. If you take an exhaust air heat pump and it says 3 kilowatt or 2 kilowatt or 5 kilowatt on the box, it isn't always the case that that's a 2 or 5 kilowatt heat pump. It could be half that output, depending on the circumstances on site. And that's a real big issue in my eyes at the moment, where the stuff is being specified that is not fit for purpose because the true output of the heat pump isn't actually matching what is stays on the box, because airflows aren't as high as they should be, etc., etc. So that's towards the end. We'll kick off now and we go through what is an exhaust air heat pump and how they work and so on. Okay, they're typically used for apartments in small homes. So the go-to solution for a long time prior to, I suppose, NZEB was central plant or boilers and CHP. Still is the case in some larger schemes, but on your medium-size schemes, decentralized systems like exhaust heat pumps are still preferred. Boiler and PV systems are kind of gone by the wayside with NZEB, especially with apartments. You don't really see as many now anymore. And even rarer still, you'll find air source heat pumps on a balcony on apartments because of several reasons. One is to do with space allocation, and second of all, it might not look as nice as an exhaust air heat pump fitted into an apartment. So there are four main options, and they all have their pros and cons. Okay, so applications, the most obvious application for an exhaust air heat pump is small apartments, up to, may I say, large apartments, penthouse apartments as well. But being an apartment, you don't usually have any outside backyard if you're on the 10th floor. So where do you hang your outdoor condenser? You hang on the wall, it'll look awful. On a balcony, you're taking up valuable retail space. So the exhaust air heat pump is a good solution for apartments. Also for small houses, up to anywhere up to 150, 60 square meters, you will get an exhaust air heat pump to function correctly in a house that size. So that will cover off any of the sites and developments you see around the country at the moment. Certainly not really suitable for larger one-off properties unless it's near passive standard. You might not get one in, but 100 meter square, 140, 50 meter square, they would be okay. The other obvious solution is for a duplex above an apartment where you don't have any backyard. These are typically 100, 110, 120 meter square, and again, exhaust or heat pump slots in there quite nicely because you don't have the backyard to put in an outdoor condenser. So efficiency compared to standard systems, so your gas and solar PV combined with the PV, etc., is you get an overall combined efficiency of 110%, which is actually quite good. An old-fashioned type central plant without a heat pump, just going by boilers and bits and pieces, can be as low as 65% because of the constant circulation of high temperature water throughout the system, even in summertime. Speaking to energy suppliers and speaking to service people who service these plants, you can get as low as 55, up as high as maybe 70, but the average is about 65%. And going with a central or decentralized heat pump, be it a split on the balcony or a exhaust heat pump in this case, you're getting easily
Have we lost him? Are you there?
Yeah, I think we've lost Mike. Just give it a second so can you reconnect.
He must have plugged out or something by mistake.
Yeah, just give him one second.
BERAAI on channel 2. Does that keep shouting?
Right, just a technical issue with Mike there. He's just reconnecting, so give him a second. He should be back on.
That's great. Thanks, Ali.
And sorry there, my laptop died. I forgot to plug in the laptop.
You're grand, Mike. It's no problem.
You're back on again, Mike. Off you go.
Can you share it? Can I share again there, so?
Oh yeah, sorry.
Where are we here?
Yeah. We're back, I think. Yeah, great.
Great. Apologies there, guys. I forgot to plug in my laptop when I started the presentation and it just happened to die, of course. Anyhow, I keep going. So exhaust heat pumps. Some of the examples on the marketplace at the moment we'll see Neelan is an exhaust heat pump, air to air. So you don't need rads. It supplies warm air to the apartments, extracts from wet rooms, supplies warm air back into your living spaces and bedrooms. Typically 1 to 1.5 kilowatts output. It may or may not need some backup electric heating. So that's an option. My camera's off. Doesn't matter.
Just on you, Mike. We can see your screen. Now they're back. Yeah,
okay,
perfect.
Great. Okay, the other one is the dual Victorum, around probably 3 or 4 years now. It's a small 1 to 1.5 kilowatt exhaust heat pump with a separate pre-plumbed cylinder. Zender is not really well known in the country for supplying exhaust heat pump, but there's a few of them kicking around. Comfort Zone, again, in the last 2 or 3 years has made big inroads into the market, exhaust heat pumps, and NIBA, which is around a very long time, probably the longest in the country with exhaust heat pumps, going back to probably 2003 or 4 with exhaust heat pumps, so they have a long standing pedigree in the country. But yeah, they're the maybe 2 or 3 main players in the country at the moment supplying exhaust heat pumps. Just how it works, if you go to the Neelan system, so you extract from the wet rooms, from kitchen, ensuite, bathrooms, whatever wet room you have, could be 2 or 3 wet rooms. The kitchen will typically get 13 litres per second, and the en-suites and bathrooms will get 8 litres per second. You install the vent air duct to the outside. That's cold air. That can be as low as -15, -20, high as 5 degrees, depending on the demand and duty of the system. But that air duct going out to the outside is really, really cold, so it has to be treated with proper insulation to protect from condensation. So you install a secondary duct system supplying warm air to your living rooms and bedrooms. You don't need underflow heating, or you don't need rads. That is probably one of the big attractions with the Teahan system. The output is limited though, because the extract volume is quite low, because you can only recover so much energy from the exhaust air, because your ventilation flow rate, 13 in the kitchen plus 8 in the bathroom plus 8 in the WC, is just shy of 30 litres a second, and that is a limited amount of energy. So you may need to have a backup electric heater in your main living space to compensate the lack of output from the heat pump. Okay, the Juvitorum is a very similar system where you extract from wet rooms. Again, at around 22 degrees Celsius, 21 degrees Celsius, from kitchens, en-suites, etc. You install again a dump air duct to the outside. This system dumps out around +2 to +5 degrees Celsius. So again, cold air in contact with warm air has to be insulated from condensation. Most important, even a small tear in ducting, insulation we call drip over time and called damp patches on ceilings, which you don't want to see. So insulated ducting is very important on the dump air. Rads are underflow heating fitted. The output is limited again by the volume. So that's the one thing we go through with the end on the true output of heat pumps. So any heat pump, including NEBA, Comfort Zone, Joule, Teahan, they all have limited outputs based on the air volume. The max output of this heat pump is roughly 1 to 1.8 kilowatts. It may need electrical backup during peak loads for hot water heating. If your apartment is kicking out, needs about 1 to 1.5 kilowatts, you may need to have electric heater for hot water. The other exhaust or heat pump or air-to-air heat pump you might see in apartments is a simple air-to-water heat pump for producing water only. So again, you extract from your living spaces or your wet rooms, or it could be just straight from outside. And you install a dump air duct again, which is cold air. A gas boiler, of course, is needed because it doesn't provide space heating, or you need an oil boiler, gas boiler, district heating system or something, or electric heating. Again, the output is 0.5 to 1.5 kilowatts. The hot water time is slow. It could take up to 5-6 hours, but it's running all day long, so it doesn't really matter. Comfort Zone. Again, you can see a trend here, all very similar. You install a ducted system from your wet rooms. Dump air going out in the Comfort Zone is actually very cold at -15 degrees Celsius. I've seen it go as high as low as -20 at cases. So again, at that low temperature, it is vital to make sure your ducting is properly insulated the whole way out to the external of the building, not just to the inside where it hits the cavity wall, the whole way through that, because if it condensates inside in the cavity, you're going to get damp passing through eventually. So cold air is the biggest problem here. Again, you install traditional radiators or underflow heating to your heat pump. The output comes from 3.5 kilowatts up to 6.5 kilowatts. So at 6.5 kilowatts, you will heat a fairly decent sized apartment or a decent sized house based on 30-35 watts per square meter. You're looking at over 170 or 80 square meters. It shouldn't need any electrical backup for space heating and hot water heating because the output's quite big on this particular model. You're getting decent fast recovery in hot water. NEBA, again, it's almost a carbon copy of the Comfort Zone heat pump, where the output is up to 5 kilowatts. You usually don't need backup heating for hot water or space heating because the output's up to 5 kilowatts. Fast hot water recovery. Again, the very same scenario, -15 degrees leaving on the dump air here. So very important to make sure it's highly insulated. These ducts here coming from the kitchens and wet rooms don't need insulation because it's warm air. Just a quick 3D snapshot of how it looks in a real life job. So there's your heat pump, extracting from the kitchen, extracting from utility, and extracting from a bathroom or ensuite. To bring fresh air in to the building, you can do it a couple of different ways. Traditionally, you would see passive wall vents in your open plan living kitchen area. One in your main living room and one in each of the bedrooms, so one here and one here, bringing fresh air in to the living spaces and being extracted from wet rooms. Again, this needs to be calculated under the new NZEB Part F guidelines. So you have 13 in the kitchen, you have 8 in the bathroom, 8 in the ensuite, and maybe 6 in the utility. And then you need to balance these wall vents using an air manometer to get the right airflow when the system is up and running, to make sure you're not getting under ventilation in your living spaces. You can also use trickle vents in the windows, or not trickle vents, sorry, but perma vents. They're not as reliable because you can't really measure them, or you can't really accurately adjust them, whereas modern passive vents have usually a little closure in them. You can open and close the iris to set the airflow in them. So there's your basic functionality of your exhaust heat pump, extracting from wet rooms and bringing fresh air in through your living areas at a controlled rate. Very similar to DCV or MEV. Just a few pictures of some first fix and second fix. So there's a manifold above a utility room. You have your extract from your kitchen here, and you have an extract from a utility and extract from a bathroom. The reason why you have 2 in the kitchen is because you have a much higher airflow at 13 litres per second versus 6 or 8. So therefore, bringing 2 parallel ducts to the one plenum gives you a better airflow rate at the same pressure drop. Here, ducts then going out to the outdoor or out to the outside have to be lagged properly from condensation. Again, it's another picture of a job. I think it's over in Bonnet Street in Dublin for Dublin City Council, where the contractor, in fairness, he mocked up the installation in his own warehouse before he went on site to see where exactly the ducts would fit in a row, pardon the pun, and to see where the manifold would go and what size duct you need. So you can see here, this grey duct going out to the outside is a flat pack, which is fine too. It's 204 by 60, and it has pre-factory insulated insulation around it. And the last connection here is also insulated, but it's also a flexible duct to remove any vibration transferring from the heat pump into the fabric. And also coming back here from the extract system from the manifolds, you have an insulated sound attenuator. So this attenuator will kill about 3 or 4 decibels off of the fan noise coming down through the ventilation system. And that is vital, because if you have your fan is up here and that noise can transfer down the duct system into your wet rooms, which can be heard throughout the apartment if it's not done right. And I've done a lot of commissioning on heat pumps, on exhaust heat pumps over the last number of years. And if you go to a job and they forget to fit the attenuator or didn't bother fitting it, or oh, that costs an extra €40, we won't bother fitting it, you can tell the difference. The noise level is much higher. So we always insist on having the last connection to the exhaust heat pump fitted with an insulated flexible attenuator. Again, some screenshots of first fixes and some second fixes. Manifold types, it doesn't really matter as long as it's a decent manifold. This is a metal box manifold. This is a foam manifold. 75mm semi-rigid ducting going off to your different wet rooms. Plenum boxes, it doesn't matter. Any shape or format is fine as long as it has the right airflow through it. Okay, so let's say you didn't want to have holes in the wall. You didn't want to have trickle vents or passive vents in your bedrooms. We have a job at the moment where we're working on where there's a planning condition that they didn't want to have any wall vents in the bedrooms or living rooms for 2 reasons: for noise pollution and for the location towards the M1. So this is a solution that a couple of companies have. It's a supplier module. I think NEBA have one and Comfort Zone do one as well, where you take one fresh air in, and it sends out warm air to your bedrooms and your living rooms via ducted system. So again, you extract from wet rooms as previously. You dump the cold air out. You bring fresh air in through one duct, and it goes into a heat exchanger, a warm water battery. So you take 2 half-inch pipes from your heat pump up into this box, and that box then has a water battery which preheats the air to maybe 17, 18 degrees inside in your bedrooms and living rooms, along with your radiators as well, of course. It's not a heating system, it's just pre-conditioning the air coming into the apartment that's not cold. So this removes the need for your multiple passive wall vents. Again, it's a bit more expensive option, but in some cases it actually works out the same price, because on a very, very high building above 18 meters, you now have to fireproof each of your wall penetrations. So if you have 4 wall penetrations to do because you have 3 bedrooms and maybe a living room to do, those penetrations could cost anything from 300, 400, 500 euros per penetration to core and fireproof. So 4 times 500 euros is €2,000, and that more than pays for this extra add-on. So it's a nice solution, which means you get a balanced ventilation system as well. Just to see what it looks like and finished. There's your balanced supply air system with a filter, and the door comes off for accessing the service. And there's your exhaust or heat pump fitted. Again, just to give you a 3D representation of what it looks like, there's your exhaust or heat pump as previously. Again, the same ducting, extract from the kitchen, extract from the utility, extract from the ensuite or bathroom. You're bringing fresh air into this unit here from the outside, and you're dumping the air, bringing fresh air in here and dumping it back out here. So it's a nice balanced ventilation system supplying warm air into your bedrooms, living rooms. You can see the ducting going here to give to living space, ducting into the bedroom and ducting to your bedroom, and you remove the wall vents. Okay, so to summarize what exhaust or heat pump is, just of time as well. So it's really a 3-in-1 system. You have ventilation like DCV or MEV extracting from your wet rooms. You can have the fans, and most models can be offset and set back for low mode and boost mode and so on for your ventilation. So it complies to Part F from all that aspects. Hot water, most these exhaust heat pumps can provide hot water up to 55 degrees Celsius, no problem. And they all have electric heater backup to do your Legionnaire cycle once a week, as you would have with every other heat pump. Majority of them are hot water parity, starting from 1 kilowatt to 6.5 kilowatts. So you get a nice coverage of apartment and house sizes within that power range. Most of them will be all weather compensated, so your rads or your underfloor heating can be weather compensated. Again, like most modern heat pumps, they all come with online control and energy management and all that kind of stuff. Again, is it worth it, the online control? Maybe if you're built to rent and you have a management company and you want to monitor each apartment remotely, if you get an alarm on a heat pump and apartment 14 has an alarm, instead of waiting for an angry phone call from a tenant saying, look, I have no hot water, what's wrong here? This heat pump is after going out again, an alarm. You can preempt that phone call by having it on your system to get an alert saying that, okay, apartment 14 has a hot water issue. You can then either ring the client and say, press this button and it's fine, or you can actually go to site, pre-armed with what you need to do. So the online control is fine for management companies, but for the individual person, people rarely use them, to be honest with you. Okay, but what happens when it goes horribly wrong? Which you can do. Now, I won't name names here of any supplier because it's not fair, but this wasn't the supplier's fault. In the UK a number of years ago, this person here was faced with massive energy bills over a very short period of time. It was featured on Rip Off Britain, and it shocked the heat pump industry, and it caused an awful downturn in supply of these heavy heat pumps in the UK, and they're only starting to recover now after all these years because of what happens when it goes badly wrong. The heat pump was only outputting a maximum of 1.6 kilowatts max on this particular exhaust heat pump, and that's a known fact. But these houses needed 6 or 7 kilowatts. So the immersion heater that was fitted in with the heat pump was 9 kilowatt, and of course that ran for several hours every month. So in that case, that heat pump was not the right choice for that house, or those number of houses in that site, which was quite a lot of houses. They're far too small. There was no design consideration taken for heat losses. Literally, the building contractor came in and said, yeah, I want 40 those heat pumps there. They look fine. We'll take 40 those. And they were installed with no proper ducting being used. What they used was light gauge ducting that you'd see off of a clothes dryer, not proper ventilation ducting. The homeowners were also on prepay meters, which are, again, the dearest meters you can get. So bad news travels fast. So we want to try to not happen in this country where exhaust heat pumps are installed correctly at the right size, the right output, and not to be, going down the road of, oh, these things are a disaster. They're not working. They're not great. I have high bills. We don't want that. So it's very, very important that the next section, this presentation is looked at very closely, where we can see the true output of an exhaust heat pump. Okay, so when we're putting this into DAP, the first part of DAP is the same for everything. You're putting your fabric losses, your walls, windows, doors, core bridging, all that stuff. It's all pretty standard and same for every job. Next, when it comes to the ventilation tab, it changes a little bit. So finally, after years of hounding SAI, they gave us a drop-down box from exhaust air heat pump. Okay. Originally, we had to use the SAP Appendix Q for the fan power. That is now gone. Why? Because the fan on the exhaust air heat pump is doing two jobs. It's doing the ventilation system for the house, but it's also doing the heating of the hot water and the ventilation, or the heating and hot water as well. So it's doing two jobs. In other words, you wouldn't put the fan power from a Hitachi split into your ventilation system. Why would you? But in the exhaust air heat pump, we were asked to do that. We were saying that's not fair, because the fan power has a huge impact on your overall BER. Some things don't, but the fan power did. So what we said was, okay, how long is a piece of string? How often is the heat pump not running but the ventilation's running? No one can calculate that. So in fairness, the SCI gave us a default figure for exhaust air heat pumps. And if you pick exhaust air heat pump, you'll see that 0.26 will pop up straight away. I have an email if anybody wants that from SAI to show that this is the case. So you don't go to SAP Appendix Q anymore. You use 0.26 for all exhaust air heat pumps. The next one is you need to use the exhaust air flow rate that the heat pump was tested to. So in this particular model, in this example here, the exhaust air flow rate tested was 180 meters cube per hour. That's what you have to use. There's no other way around it. If it was tested 160, use 160. If it was tested 200, use 200. Okay, next page. The same page. Sorry, next page. If you had this model I showed you a while ago, the supplier module, how does that fit into DAP? Because it's not a typical MVHR. It's an exhaust air heat pump with a supplier module. This took about 6 months of back and forth questions with SAI to get a simple, very, very simple answer. And the answer is you tick that box there on the left-hand side that says warm air or fan coil present. Because it is, in essence, a large fan coil. It has a warm air battery inside it, and it has a fan blowing out warm air to your living rooms. So after about 50 emails and 40 phone calls, we got that answer from them, and that box you tick, and that puts in a notional fan power and kilowatt hour a year for that supplier module. Okay. The next thing inside the control responsiveness, again, it's very, very similar to a traditional heat pump. So you pick your central heating systems or underflow heating, you pick heat pumps, again, a new category, exhaust air heat pump, emitter type radiators, time and temperature controls, if you have them or not, weather compensation, yes or no. If you have it, majority, 99% of the case is going to be yes. Pumps and fans, again, we can use a formula, and the formula is here. So you take the control type, is the boiler in this case, is the heat pump controlling the circulating pump, yes or no? If it is, then what is the power of that circulating pump? Let's say it's 40 watts or 50 watts or 60 watts. You multiply it by that and divide it by 65, it gives you a kilowatt hour per year for that circulating pump. And in this case, it came up with 26. So the default would be 130. And again, that has a big effect on the overall output, the overall BR report. So if you have the known power of the circulating pump and it is controlled by a room stat or a boiler, whatever it is, you can then use that formula to give you your kilowatt hour a year. Okay, next thing is to add your heat source. Again, you add the heat source the very, very same way as you would with any other heat pump. You add it into the library. So in this case, this is also a heat pump. It also heats hot water. Okay, so you tick the box for heating hot water. Put in your design flow temperature. In most cases, we would size rads to 45. In some rare cases, maybe 40, but they get quite big at 40 degrees Celsius. Believe it or not, 5 degrees has a massive impact on the radiator. It could be up to 25, 30% bigger. And in some cases, you don't have the wall space for it, or it just looks wrong. So 45, 44 is about the norm for rads. The operation is normally 24 hours a day. In this case, it has the internal hot water storage because it's all contained in one package unit. and you pick your electrical backup. In this case, 99.9% of the heat pumps will have electrical backup for hot water and heating. But make sure you tick the box that says heat hot water, because it does. Okay, then we all know this. You put in your low temp test conditions, so your air -7 to 712 and your TOL as before with any heat pump. Again, your mandatory height, your high temp 55 data as would before any other heat pump. Then you put in your NWH figure, your nominal and hot water efficiency figure. In this case, it's 118%. Power of the heat pump, standby losses, reference hot water temperature, load profile, and your test of the hot water, your test volume of the hot water cylinder. In this case, 170. So there are 6 conditions you have to enter. Again, as you do before, you put in how many mixing showers you have. Is it unvented, vented? How many bathtubs you have? In this case, it's 1 bath and 1 shower. They are distribution losses because you're sending water out through the system. There are storage losses because you have a domestic hot water cylinder, and that's, as far as that goes, that's that section filled out. And next you pick, is the hot water storage indoors? Yes, it is. Now, they do call it, which is very, very strange. You don't have a drop-down box yet for exhaust or heat pump or split heat pump or monoblock heat pump, which I'm trying to get them to do because it's very hard for us to figure out what the hell is this considered as. So in this case, it's called integrated terminal store and gas-fired CPSU. For whatever reason, I don't know, but that's what they call it. Storage volume, internal hot water storage. Manufacturer, in this case, was comfort zone, disclaimer losses. Is there a separate timer for hot water? Yes, there is in the store. Is it in the cupboard? In this case, it was. We didn't have testing for low hot water usage. Okay, and you should get your efficiency up on your hot water without any alarms. If you have an alarm on any of these, you go back and you see what went wrong. But in this case, we're getting 251, which isn't too bad. Okay, and you should, at the end, as we all know, what you see, you should see your green ticks throughout the compliance. I just see, is there any question there? I think I see something there, Ali. 55. There's a question here about default 55 should be entered. Yes, you can use any temperature you want on the radiators as long as you provide the detailed SR50 heat loss calculations room by room to prove that the radiators are being sized to 40, 45, 50, whatever you want, but 55 is the default. If you use 55 degrees, you will find you're getting very, very hard to get your EPC tick in the box because the efficiency of the heat pump will drop off quite a lot at 55 degrees Celsius. So as long as you're sizing the rads to a low temperature, you can provide that proof with using the SR50. The primary circuit losses are always set to yes. Think of that in here. Oh, sorry, primary circuit losses to no, because again, I got this from SEI, it's inside in one contained one unit. So there's no outdoor unit sending in water to the cylinder, or no boiler going to the cylinder, or it's not a monoblock heat pump with a unit that's 10 yards or 15 yards away. It's literally within the same contained box, so you can put in none from your primary circuit losses. Okay, that's that part of the presentation done there. So what I'm going to do is go to the next one, which is the spreadsheet showing the exhaust or heat pump outputs.
Just before you move on, Mike, there are a couple of questions in the chat. If you want to take them up there now, just while it's fresh.
Okay. Electricity consumption calcs for a circulating pump are out of date. I think we are using EEI now rating. I'm not too sure on this, Moss, but the DAP manual still, even the DAP 4.2 manual still shows the calculation methodology for that. You're taking your your factor inside in the table and dividing it by 65 and multiplied by the power of the pump and so on and so on to give you your kilowatt hours a year. I can certainly ask that question, but the 4.2 minus still shows that formula. Can you give some kind of flow area? Let's say for part L, some rule of thumb would be max area possible for exhaust heat pump. Good question. The max area really is down to your fabric losses. Again, the exhaust heat pump could potentially do a building that's 5,000 square feet if you're building a passive building with 10 watts a square meter, you know, Liam. So if you have a certified passive building, it's 500 meters square. Why not? The heat loss is only 5 kilowatts. But again, you know, they're not going to happen. If you take 2019 part L, sorry, I never read the last part of the question. You're looking at 30 odd watts a square meter. So if you take a heat pump that has a 6 kilowatt output, 6,000 divided by 30, that's, you know, potentially 200 meters square, which is a large single family home. So yeah, exhaust heat pumps can fit the majority of reasonably small to medium sized new builds. Okay, so going back to this spreadsheet here. So you might have seen this before. So I built this spreadsheet over the last 12 months or so. It's a detailed room by room heat loss calculator, which now builds in a lot of things like exhaust heat pump sizing, exhaust heat pump outputs, rad sizing, underfloor sizing, ventilation flow rates as well built into it. So it does give us a very good picture at the end what's involved. So again, as before, this is slightly changed. My first page here is just for the kitchen and living area combined. So if you have a kitchen combined with a living area, the kitchen has its own flow rate and the living area has its own flow rate from a ventilation point of view. So this here, you put in the kitchen area and the total area, and it works out the mixed average ventilation rate, and it gives you a kitchen area and other living area separately. This is more important from the ventilation section down the line, but it's a bit more accurate than just having one area. Again, you put in your second room, third room, so on down along, and we get to our.
I can't see your screen there, Mike.
Oh, it's shared. Oh, sorry, my mistake.
Thanks. Okay.
You see it now?
Yeah. Yeah.
Okay. So yeah, I go to my exhaust heat pump tab here. Okay, right. So if I pick apartment here, which I've done a calculation on before there, if I pick, let's go back here and show you. If I pick this living room here, it's an open plan living room, kitchen, dining area, it's 40 square meters. The fabric, just to go through the fabric, it's 0.15 in the floor, 0.18 in the wall, 0.16 in the roof, 1.4 windows, 1.4 doors. So it's part L 2019. Exhaust air heat pump, 8% core bridging, 2.45 meter high roof ceiling. So it's typical 2019 building. So there's my kitchen, living room at 40 meters square. It has a floor loss. It's in the ground floor. It's a living room. My kitchen is part of the living space. Yes, it is. It's 10 meters square. So you see my ventilation here is slightly changed. If that was 0, it goes to 0.65. You can pick a ventilation type, so it's part L. So if I pick my kitchen is 10 meters square, my ventilation changes slightly because it's getting a higher airflow in the kitchen as a proportion of that room. So my ventilation loss there is 582 watts. The external wall area is length is 11.8. My windows are here. There's my heat losses. And my total loss in that room is 1.321 kilowatts or 33 watts a square meter. Go to my second room, my hallway. Same idea again, your windows and floors. That room is a heat loss of 22.9 watts because it's very, very small external wall. Utilities room is in the middle of the building. It has no external walls, so 0. 15.3 watts a square meter. What's next? The bathroom. Again, 19.7. So you get the idea. You do each room individually. And you come to the last room, which is, I think, bedroom 2 is the last room. Yeah, bedroom 2. So there's my 7 rooms in that apartment. You go to the very end here. And you can now pick a rads. So I'm going to pick a floor temperature of, say, 40 degrees. If if I go to say 40 degrees and I go to 35 on return, what was now big enough red, two 1500 doubles, is now only showing 79%. That must be a much bigger red. Let's say two 1800s, no, two 2000s. I'm now getting my red big enough. So by going from 45 to 40, I'm going up my red quite a lot. If I go back to 45 again on the flow, and I go 40 return, I'm 146% over, so I can bring them reds down quite a lot. Maybe 1200, no, 1500, yeah. And go lower, 14, yeah, 14. So there, two 1400 doubles will give me my power coverage for that room at 45 degrees flow and 40 return, with a heat loss of 33 watts per square meter. Two reds in that room. The rest, it was saying you pick a red size, be it double or single or whatever it is, or triple red, to give you your coverage in that room. It gives you your total heat loss here at 2.468 kilowatts, of which 47% is fabric losses and 44% is ventilation losses. Give me a HLI of 1.18. Okay. Then I've also built in here as well to give you the amount of flow rate in the water system. So you're looking at 0.343 meters cube per hour of water flow rate through those reds, based on standard K2 double panel reds. Also on the right, you have triple reds, 300, 400, 500 high as well. If you go down, you have aluminium radiators, so two sections at 16 sections each, or 600 high reds. On the floor as well, same before, you pick your mean flow temperature, 30, 35, 40, what it is, 30 degrees flow. And if I change my flow covering here to, let's say, carpet, no good. My output on my floor isn't high enough. I have to go to 35 to get my temperature in the floor hot enough to get my room heat loss covered. Back to 30 and change that back to carpet or to tiles. And then I get my green boxes throughout each at 100 centers, 150 centers, and 200 centers. And then it gives you a report, and at the end, then giving you your room details, your single reds, double reds, 500 high, 600 high, and triple reds, and also reporting for heating how much pipe per meter you have, how many manifolds you need, and bits and pieces. Now this is new tab, which is the new Part F guideline. So when you're putting in your either exhaust or heat pump or advanced MVHR system, you need then to work out, as part of the new NZEB, you need to work out the airflow per room. And this tab here, this section, this table, pulls all the information from the previous 15, 16 tabs into one page here. So this is my kitchen only area. The rest of that room was 30 meters square, as you see from previously. So that's 10 there and 30 here. If I go back to my room one. Room one, my kitchen was 10, my rest of the area was 30 because my total area is 40. So back there to my MVHR section. Okay. If you pick how many people you have, say there's 10 people, that'll change the ventilation rates because the 10 people is now the bigger figure. So if you look here, the guidelines are 0.3 litres per second per square meter. So that gives me 26.085 litres, which is down here. Kitchen plus wet room. So I have kitchen plus 1, 2, 3 wet rooms. That gives me a value of 35. Exhaust or heat pump is 35. So the greater is out of all those is 35, and that's what's used as my minimum ventilation rate. And the boost in is 25% higher than that. So then inside this table here, you pick which type of room it is. The hall, is it a bathroom or a kitchen, or is it another type of room? And that'll give you your supplier. So in my hallway, I need 5.28 litres per second in my hall and 6.6 on boost. In my utility, I need 6 litres per second on minimum and 7.5 on boost. In my kitchen, 13 and 16.5 and so on and so on. If that was a higher occupancy building, let's say it was 8 people inside it, then you see this here slightly change because now the per person rate is now the highest rate out of all of them. Therefore, that is the rate I'm going on, 37, not 35. Again, if that was higher, say it was 10 people, I'm now looking at a minimum rate of 45. Therefore, my minimum and my boost ventilation rates have gone up quite a lot. And this gives you your total volumes, your total supply air, your total extract air, so you can balance the system properly with your air manometer at each point and get the system balanced properly to comply with the new NZEP guidance. So in this case, it's a 5-person occupancy. So that means my kitchen plus 3 is the higher of the ventilation rates, and that's my baseline. I use 35. Now, this is the most important page. So let's say I take the comfort zone heat pump, for example, right? And I have a ventilation rate of, as this pulls this 35 liters per second, pulls this from here. All right, pulls it in from here because that's the greater R. So I'm using 35 liters per second in my ventilation. My apartment was 86.95 square meters with a ventilation at 35 liters per second. I'm sucking in 22 degrees of air. I'm blowing out minus 15 degrees of air. My compressor power is 1.1 kilowatts. Therefore, my enthalpy, which is the amount of energy in the air at plus 22 degrees, is 37.586 kilojoules per kilogram. At minus 15 degrees Celsius, going out at 95% humidity, my enthalpy is minus 12.697 kilojoules per kilogram. Therefore, that heat pump is providing, via the exhaust air only, 2.137 kilowatts. That's it, no more, no less. How that's calculated is your enthalpy difference, which is 37.586 minus the 12.67, which gives you 50.28 kilojoules per kilogram, times the density of the air, times the heat capacity, times the ventilation flow rate, which in this case is 0.035 meters cubed per second, which is 35 liters per second. And that gives you your amount of energy in that exhaust air. Nothing else, nothing more, nothing less. You add that into the compressor power, because total energy in equals total energy out. That gives you a total output of that heat pump of 3.2 kilowatts, even though the box might say 3.5 kilowatts, not the case. If that was a smaller apartment and I was using much less airflow, let's say I dropped that, I overwrite the formula and I put in, say, 21 here. Okay, because I'm getting less airflow, my enthalpy has dropped quite a good bit. I'm now getting 22 in, minus 15 out, but my airflow is only 26 liters a second, or sorry, 21 liters a second. 21 liters a second. Therefore, my exhaust air heat pump is only giving me 1.28 kilowatts plus my compressor, which is 2.38 kilowatts. Therefore, it's too small. Okay. If that heat pump was venting out, say, at 0 degrees Celsius, then look what happens. Because I'm not taking as much energy out of the exhaust air, I'm not squeezing the air as much. Therefore, my enthalpy has gone from minus 12 to plus 8. Therefore, my enthalpy difference is not 50 anymore, it's 28.6. And the calculation is the same. The enthalpy difference times the density of air times the heat capacity times my airflow gives me my exhaust air potential. And that's just shy of 800 watts. Plus my compressor power gives me, boom, 1.8 kilowatts, which is way too small for my apartment. Again, if I increase the airflow to say 50, sorry, 50 here, sorry, 50. Okay, it's big enough, right? But now you see my air change rate. My air change rate has gone from 0.5 in air change up to 0.7 in air change, 0.77, nearly 0.8 in air change. Therefore, I've just increased my ventilation rate by quite a bit to make the heat pump powerful enough to heat my apartment, because my vent air is only 0. Therefore, I have to go back now here and change all my ventilation rates to 0.7, which means my heat loss is going to go up. Do you get what I'm trying to say here? The higher the ventilation rate is, the more heat losses you have, therefore the more output you're going to need in the heat pump. So you end up chasing your tail sometimes with the exhaust heat pump. But if I dump out here at minus 15 now, I'm well covered. I can bring my ventilation rate back to 35 as it was previously, and I'm covered because I squeezed the air from 22 to minus 15, and therefore my air change rate is back to 0.5, which is normal and not over ventilating. So my point here, the most important part of this slide here, if you take anything else away from today, is that what the heat pump badge says be it NEBA, Joule, be it Comfort Zone, Neelan, whatever it is, doesn't matter. The NEBA heat pump might say 5 kilowatts, but it might only be 2.5 kilowatts in reality, because the airflow rate is only 35 litres a second and my enthalpy difference is only 50. If, yes, I had a larger penthouse apartment that's 180 metres square, and I have 6 wet rooms and I have loads of ventilation rate, yeah, for sure, I'll get 4.5, 5 kilos or my NEBA heat pump or my Comfort Zone heat pump. But I certainly won't get it out of a smaller 1 or 2 bed apartment. My output is way less than what the box says. So you should never go by what the badge on the box says. It's a 5 kilowatt heat pump or a 2 kilowatt heat pump or whatever it is. Not the case. You need to do a calculation like this to say, okay, is my heat pump actually big enough with the exhaust air to heat my building? If it's not, what's going to happen is, like happened in the UK, you're going to end up having lots of immersion heaters kicking in at one time, using up lots of energy because the ventilation calculation wasn't done properly at this design stage. So this took a long time here to build this 1 page alone with the psychometric chart and the enthalpy calculation, so on, to get this working right. So when we're doing any design on an apartment, we'll always look at, okay, what heat pump will actually work in this apartment and get me my coverage that I need. Even though it might say 3.5 kilowatts, I might be getting 1.5 because it's a small 1 bed studio. All right, so I think our time is nearly up there, I think, Eleanor. So if we have any questions, we can take them.
Yeah, we have just 1 or 2 questions there in the chat. Does the ventilation boost and humidity or override switch?
You can have lots of different heat pump exhaust heat pumps. For start, they're always running because they're a heat pump in essence, not like a DCV system or an MVHR where their one job is to ventilate. The exhaust heat pump has 2 jobs. It's to actually 3 jobs: to ventilate, provide hot water, and also to provide space heating as well. So the fan is always running at a certain speed, which is the minimum Part F ventilation rate. And yes, you can install humidity sensor, or you can install a PAR, or you can install a motion sensor, whatever you want, to activate a relay in the heat pump to bring it from normal rate to boost rate for 1 hour, 2 hours, 5 minutes, whatever you want. So you can do that with either a humidity sensor or a PAR motion sensor.
Brilliant, brilliant. Anyone else there, guys? Feel free to unmute yourself if you'd like to talk, or anyone.
Yeah, it says here, user 22 degrees, but it's only available when someone is having a shower. Not the case. I'm sitting here in my house here at the moment in my office, and it's 22 degrees in my wall here. So it's the case, the exact same thing, middle of winter, my house or my apartment will always be 21, 22 degrees Celsius. So if you drop that down to 21 degrees, you're such a small minor difference on the entire calculation, it's not even worth it. But you get most people, and I've learned, they don't like 20 degrees, they like living in warm houses at 22, 23 degrees Celsius. So you'll find most apartments, because of the nature of the apartment, most apartments overheat for most of the year anyway. So 22 degrees would be quite common. It'll go up to, what will happen is in the shower, you're going to get a higher humidity, which means you're going to get a higher latent heat at the heat pump, which means you're going to get more energy out of it. But that's another story. But yeah, having the extract from wet rooms is only a bonus, but you get 22 degrees all the time.
Mike, Chris Moore here.
Chris.
Just wondering, the temperature of the exhaust heat pump.
Yeah.
The lower that is, it seems to increase the efficiency overall.
I wouldn't say the efficiency, Chris. I'd say increase the output.
The output, yeah. Sorry, the output. Yeah. What I meant. Is that something which is reflected on the data feed for each heat pump?
No, it's not, and that's the problem. Feed data is paper won't use ink, right? I can give you feed data if you want for any heat pump that'll show massive figures, right? Because you can test it in certain ways and you can do certain things with it. It's like driving my car. I came up from Dublin a while ago and I got 55 miles to gallon because it was busy traffic. I was driving nice and slow. I go up tomorrow morning, I put the foot down, I get 30 miles to gallon. So the feed data is only a snapshot under certain test conditions. The reality of exhaust heat pumps is that they don't always perform as what the data badge says. because so many conditions affected the temperature in, as stated a while ago by the user there, 22 degrees. If that was 14 degrees, for example, and startup, or let's say you start up the heat pump in the 1st of January and it's -2 outside and the apartment is 5 degrees Celsius, which can happen, then the output of the heat pump is nowhere near what's on the box. It's going to be a lot less than that. So the exhaust heat pump feature data is not a reflection whatsoever on what the actual heat pump is. You need to sit down and do this calculation, and I've made it very easy with that spreadsheet. To be honest with you, it does it for you, and you can see whether or not my NEBA or my Joule or my comfort zone or NELA, whatever the case may be, is actually big enough to heat my apartment under certain conditions.
Right. Okay. Thanks for it.
So yeah, but dropping the temperature down, it's like getting a sponge inside the bathtub. You put a sponge in, you fill it with water, you get it, you give it a small squeeze, you get a spout of water out. You squeeze it really hard and get more water out. The same amount of water as a sponge first day. There's energy in air. You squeeze it, you get some out. You squeeze it harder, you get more out.
Right, but the more efficient, presumably the more efficient heat pumps are able to squeeze more energy out of it. Is that the way that works?
It depends on how they're designed. Some heat pumps don't let the dump air go below zero because of defrosting issues or defrosting conditions that they don't have or do have. And therefore, the enthalpy difference is quite small. Therefore, the real output is actually quite small. Some machines go as far as -20, some go +5, some go -5. It depends on the manufacturer, but that isn't in the feature data.
No, but if it can squeeze more energy out of it, it's going to increase the capacity of the heat pump.
Correct, yeah.
Right, so you should be looking for a system that maximizes the amount of energy it can extract from the air.
Exactly.
And how do you know that from?
That's a good question. You won't unless you start asking questions, to manufacturers.
Okay.
What is the vented air temperature?
Okay.
And then do the calculation.
And there's no way of establishing that from product data.
Probably not. No.
No. Okay.
Probably not.
Thanks, Mike.
Can I ask?
Like I said, you inside there, Liam. 1 second. Like I said, you buy a Hitachi heat pump tomorrow morning. It says 9 kilowatts. You're going to get 9 kilowatts all day long. You buy a comfort zone or buy a NEBA, you're not going to get 3.5 or 5 or 4. You're going to get what you're going to get from the apartment. Sorry, Liam. Should on that.
Yeah, I was just bearing in mind what you were saying there, Mike. I mean, it seems to me that you wouldn't be fitting these anywhere where you didn't have an air tightness test. Is that a fair,
Yeah, you do, because you need to be fairly accurate about your heat loss calculation, Liam. Here, if you get this wrong, you can get it badly wrong with these offshore heat pumps. Not that they're a bad product; they're fantastic. I actually love them. They're really, really good once they're put into the right application and the right building. If not, you're opening up to a lot of immersion heaters kicking in unnecessarily and angry phone calls from people saying, "My bill was 500 quid this month. What the heck happened?"
Yeah.
And that's you don't want, because then they all get tarnished with the same name. Like when I restarted off doing exhaust heat pumps after a long time of not doing them, and into a big consulting engineering firm in Dublin. I won't mention the name. I got fucking lambasted about exhaust heat pumps. Are you having a fucking laugh? These things are a disaster. Did you see that in the UK? All these, it got tarnished with the same brush because of what happened 10 years ago.
Yeah.
Because of badly installed, badly designed, badly sized heat pumps. Not an empty heat pump. If I drove my car backwards to Dublin at 50 miles an hour the whole way, I'm not going to have a good engine left over. Is that the car's fault or my fault?
Perfect. Thanks, Mike.
Okay, guys, I'd say that's kind of it, is it? Well, I'm going to stop the record there, and we can have some more questions. So just a second there now.